Hey everyone and welcome. Today we are diving deep into the really elegant logic that stops modern computer networks from just, well, turning into a complete mess. We're going to break down how engineers use two absolutely key tools, VLANs and subnets, to build systems that are fast, secure, and actually manageable.
I mean, seriously, think about it for a second. You've got thousands of phones, computers, printers, maybe some servers, all of them trying to talk at the exact same time. How is that not a complete and utter disaster? Well, it's because a well-designed network isn't just one giant free-for-all room. It's intelligently and very deliberately divided up.
So on one side, you've got what's called a flat network. Imagine every single device yelling into the same crowded room. It's pure chaos, it's noisy, and it's a huge security nightmare. But on the other side, you have a segmented network, and that is all about creating order, control, and, most importantly, security. And figuring out how that works, that's what we're here to do.
Okay, to make this all really click, we're going to use a simple analogy for this entire explainer. Just try to keep this in your head. Think of a VLAN as a dedicated traffic lane on a highway. A subnet, that's the specific address plan for all the houses on one particular street. A gateway is the exit ramp you use to get off the highway. And the router, well, that's the traffic cop directing cars between all the different streets. If you can remember that, everything else is going to fall right into place.
All right, let's dive into our first piece of the puzzle, these virtual traffic lanes, or as we call them, VLANs. This is all happening at what's known as Layer 2 of the network, basically the world of physical switches and hardware.
So what is a VLAN really doing? Honestly, it's kind of like magic. You take one physical switch box, and you use software to basically slice it up into multiple, totally separate virtual switches. Each one of these little virtual switches creates its own isolated room, or what we call a broadcast domain. And here's the practical impact of that. Without VLANs, every single device sees every broadcast message from every other device on the network. It's incredibly loud and super insecure. But when you introduce VLANs, that broadcast traffic hits a virtual wall, the VLAN boundary, and it just stops cold. Devices are now neatly and quietly contained in their own dedicated lane. So how does the switch know which lane a device is supposed to be in? Well, it all comes down to two types of ports. You've got an access port, which connects a single device, like your PC, and its data doesn't need any special labels. It's untagged. But then you have a trunk port. Think of this like a multi-lane superhighway between switches. It's designed to carry traffic from multiple VLANs at once by adding a special digital tag to each packet, which tells the next switch exactly which lane that piece of data belongs in.
Okay, so we've built our virtual lanes at Layer 2. Awesome. Now let's move up a level to Layer 3 and see how we create the address plan for each one of those lanes. Welcome to the world of subnets.
Right, so unlike a VLAN, which is a boundary you create inside a switch, a subnet is a purely mathematical boundary. It's just a logical way of taking a big block of IP addresses and slicing it into smaller, much more manageable chunks. It defines the street name, the range of available house numbers, and that special mailbox for sending announcements to everyone on the street. Let's break down a classic example here. That 0.0 address at the beginning, that's the network address. Think of it like the name of the street, Elm Street. The .255 address at the end is the broadcast address. That's a message sent to every single house on Elm Street. Everything in between, from .1 all the way to .254, those are the valid addresses you can actually give to your devices. Those are the house numbers.
So, we have our virtual lanes, and we have our logical address plans. Now comes the most important part of all, connecting the two together. This is that aha moment where network design goes from just theory to something real and practical.
And here it is. This is the crucial point, the simple, unbreakable rule that governs pretty much all modern network design. For every single VLAN you create, you assign exactly one subnet to it. They are a matched pair. You never, ever mix them. One VLAN, one subnet. That's the rule. And here's exactly how that plays out in the real world. See, the staff PCs are in VLAN 10, so they get their IP addresses from the 10.10.10 subnet. The voice phones are in VLAN 20, so they use the 10.10.20 subnet. The guest Wi-Fi is in VLAN 30, so they use the 10.10.30 subnet. Each group has its own lane and its own unique address plan, and you'll notice each one has a gateway. That's their designated exit ramp.
So let's bring it right back to our mental model, because this is the key takeaway. The VLAN is the physical lane the traffic is driving in. The subnet is the unique set of addresses that are only assigned to the devices in that specific lane. They are two sides of the very same coin. Okay,
Now that we've built the roads and the address system, let's do something fun. Let's actually follow a single piece of data as it travels across our network. How does a PC in the staff VLAN talk to, say, a server that lives in a totally different VLAN?
All right, let's walk through this journey. A staff PC in VLAN 10 wants to talk to a device in VLAN 20. The first thing it does is check the address, and it realizes, hey, that's not on my street. So what does it do? It sends the data to its exit ramp, the default gateway. The switch makes sure to keep that data inside the VLAN 10 lane until it finally hits the gateway, which is our traffic cop, the router. The router then unwraps it, repackages the data for the VLAN 20 lane, and sends it on its way to the final destination.
Now, here's a super important technical detail that trips a lot of people up. Every network device has a unique physical ID called a MAC address. Think of it like a serial number burned into the hardware. As that piece of data travels and hits a router, the router actually strips off the old physical address and puts on a new one for the next leg of the journey.
But, and this is the absolute key, the IP addresses do not change, not ever. Think of them like the ultimate return address and the final destination address you write on a letter. They stay the same for the entire trip. And that right there is the fundamental difference between Layer 2 and Layer 3 networking. Okay, knowing how all of this should work is great, but the real test of an engineer is knowing what to do when it all breaks. So let's look at a couple of classic failure scenarios you're almost guaranteed to run into.
This is probably the single most common configuration error out there. Just imagine, a network admin gives a computer an IP address from the staff subnet, but they accidentally plug its network cable into a port on the wall that's been configured for the voice VLAN. What do you think happens?
Well, the symptoms are just maddeningly confusing if you don't know what to look for. The computer has a perfectly valid IP address, everything looks right, but it can't talk to anyone. It can't even find its own exit ramp, the default gateway, because it's physically trapped in the wrong traffic lane. It's basically screaming for help, but no one in its correct subnet can hear it.
Okay, here's another classic problem. You've got two switches connected by one of those trunk links, right? The one that's supposed to be a superhighway for all your VLANs. But what if you forget to tell that trunk link to allow traffic for, say, VLAN 30, the guest Wi-Fi?
Oh, this one is also really tricky. Everything on that first switch in the guest VLAN works perfectly fine. All the guests can talk to each other. But the moment the traffic tries to cross over to the second switch, it just hits a dead end. The trunk port basically acts like a bouncer at a club who doesn't have VLAN 30 on its guest list, so it just drops the traffic right on the floor. You end up with this confusing, isolated island that can't talk to the rest of your network. And that brings us right back home to our simple but really powerful mental model. Whenever you're troubleshooting a network problem, just ask yourself these questions. Is the device in the correct traffic lane? It's VLAN. Does it have an address from the right address plan? It's subnet. And from there, can it find its exit ramp to get to the traffic cop for routing? If you can answer those 3 questions, you can solve almost any network connectivity problem you'll ever face. Thanks so much for tuning in.